dynamic case. And so we're going to jump over to examples bar shear wave quad 4. And there's files for running static friction, slip weakening, and rate and state friction with the aging law. We have also a kinematic example in there. Kinematic slip or prescribed slip, I think is what it's called. There's a .cfg file. And so in this case, to run these examples, we need pilot spontaneous rupt.cfg to get our spontaneous rupture parameters, and then parameters specific to each of the friction cases. And so this is all on one line. It's didn't fit on one line here on the slide. The sort of scheme of this problem is that we have a big, long 8-kilometer bar that allows shear deformation. We constrain the axial deformation to be 0. We put a fault here in the middle. We're going to apply tractions with this time history. And so we're going to start out with an initial value of 75 megapascals. We're going to have a smooth transition here up to 100 megapascals of shear traction on this fault. We also have impose a normal traction. That this is going to exceed the friction criteria, so we're going to get slip. We'll generate shear waves that propagate down the bar. We have absorbing boundaries here at the ends that are going to absorb those shear waves. And there will be some very, very small reflections that come back, but they are very small because we have very good boundary conditions for normally incident PNS waves. It's only when the waves come in at an angle that the reflection coefficients are slightly smaller. And so as long as our boundaries are far away, the seismic waves tend to come in perpendicular. They also are lower in amplitude, and so we can effectively absorb the boundary conditions in these dynamic cases. So that's the setup for this dynamic problem. So we're going to go over and run it. So I need to switch over to bar shear wave quad 4. I'm going to pull up. Close all these windows. Here's my quad 4 directory. Let's pull up my pilot app file. So this is one of our first dynamic problems. We have the same sort of general output. We've added in some additional sort of debugging information. Our mesh is coming from Qubit. It's a very simple quadrilateral mesh of this 8-kilometer bar with a 200-meter cross section. We're in 2 dimensions for our coordinate system. Our problem is also in 2 dimensions. Formulation now. Instead of doing implicit time stepping, we're doing explicit time stepping because we're going to do a dynamic problem. For any reasonable problem in dynamics, we do explicit time stepping because we don't want to be inverting or doing the iterative linear solve of our mass matrix on the left-hand side. At every time step, we diagonalize our mass matrix, which makes things go much orders of magnitude faster. You use less memory. In all of our problems, we've been doing an elastic calculation at that first sort of time minus dt. We're not going to do that in this particular case. We don't because our deformation starts out at 0, and so we can just immediately jump into our time stepping. You can look at the manual for more information about this elastic three-step. It's generally using quasi-static simulations where you want to first do a static elastic calculation and then do viscoelastic relaxation. Another difference with our dynamic problems is that now we're going to use a component that's set up to do the non-dimensionalization in parameters more convenient for our dynamic simulations. So here, instead of a time scale and length scale, I'm giving it a shear wave speed because this is how I sort of determine the length and time scale of my problem. They're going to come from the the wave speeds in a problem as well as what frequency content is in those waves. My boundary conditions, absorbing boundaries on plus x and minus x. And then in order to constrain the axial component everywhere except the faults, I created a sort of all no fault boundary interfaces. I have my single fault, a single material that's going to be elastic. Total time of 12 seconds with a time step of 0.05 seconds. So you'll notice that compared to our quasi-static simulations with very large time steps, now we're going down into resolving things at the sort of millisecond type time scale. 2D problem, so we're going to use elastic plane strain. Very simple case. Material properties are in our matprop spatial database. Fiat Lagrange, because we have a quadrilateral mesh, cell dimension 2. Here I can also specify what my quadrature order is. So I'm going to use 2 by 2 quadrature so I can do a good integration of my inertial terms. And because they involve more terms in the polynomial than my stiffness terms. Here's my absorbing dampers boundary conditions. So normally I've been using Dirichlet boundary conditions to change from that default. I need to actually specify what component to use on my boundaries. Again, I give it the name of the node set in qubit. Here for my absorbing boundaries, to tune those dampers to absorb the elastic waves, the constants in my dampers depend on my elastic properties, so I give it the spatial database for my material properties, and so it'll go in and query for the elastic properties on the boundary. This is another finite element integrations, so I need to give it my quadrature information. Reduce my dimension by a factor of 1 down to 1 from 2 because this is a boundary. Use the same quadrature order. Same thing on my negative x space. For the domain where I want to specify 0 axial displacement, I can use the default 0 displacement database and Dirichlet boundary conditions. All I have to give it is 2 parameters, which degree of freedom to constrain, as well as the name of the node set in qubit. For my faults, here's my material ID for the fault, then label the node set in qubit, my quadrature scheme for my faults. Notice my PETSI parameters. In the dynamic case, there's no solver parameters because I have such a trivial solver. We don't use PETSI. And so I'm just going to ask PETSI to give me the log summary and output. So this is my pilot app that's independent of whether I'm doing a prescribed slip or spontaneous slip simulation. Let's look at my spontaneous rupture parameters. So I change here the fault type to my dynamic fault or fault constitutive model, my initial tractions on the fault surface. So I'm going to have 75 megapascals of right lateral, 120 megapascals of compressive. And then my perturbation, I'm going to do 25 amplitude of 25 megapascals in right lateral. Here's my traction perturbation object. So the default is to not have any traction perturbation. So when I want to add in, I just say, instead of, I create my traction perturbation and give it a the default is sort of a null component, which isn't going to do anything, and so I just give it the name of my traction perturbation component. I have access to the same temporal variation that I do for my time-dependent boundary conditions. So I have an initial database. This is the initial value. So for my fault tractions, I have a shear component and a normal component. I'm using a uniform database. I'm going to give it 120 megapascals of compression. So the compression gives positive values are in the shear direction are left lateral. So to flip it to right lateral, I put minus out front for my 75 megapascals of initial traction. My temporal variation, I want the 25 megapascals for the temporal perturbation. I want it in the right lateral direction, so minus 25. No change in the normal direction. I want to start at 0 seconds. So the amplitude has a start time of 0. The actual time history, because I have that smooth variation time history, I need to give it all those values. And so those values are in traction change time database. So here's my traction change time database file. Let's increase that font size so you can see it. So I have 102 points. They're all, the time stamps are in seconds. So the first column is the time stamp. Second column is my normalized amplitude. So and you can see here I have a time step of 0.01 seconds. Very smooth discretization up here to 1 second. And then once I've hit that 1 second, I have a value of 1. I keep that value all the way up to 15 seconds. So here I used a uniform time step for the first second, and then everything is constant after that. So then I stopped using a uniform time step, and I just put a big jump from 1 second to 15 seconds. So you don't have to use evenly spaced values in your time history files. You just put in the values to resolve basically the control points, much like you do when you do the spatial variation. And pilot 4 and 888 in between. Output, here I'm going to ask for the info file for my fault, give me the initial traction value, and then when you write the values, give me slip rate and the traction. Don't write the output every time step, write every other one. So that's what the skip equals 1 means. Any questions about the setup of this spontaneous rupture problem? We still have yet to specify our friction model, so spontaneous rupture static friction. This is a pretty small file in that it basically says what my friction model is. So we're using what we used in our 3D Hack-8 example, coefficient of friction of 0.6. Because this is, now I'm down into, these are specific to my static friction case for spontaneous ruptures. So here, this is where I've embedded my file names specific to this problem. And so we can run it. So pilot spontaneous rupt.cfg spontaneous rupt static friction. You'll see the time steps flying by. And so let's go to pair view, look at the results. We now need to change our directory, go up to examples, shear wave quad 4 output. So here's my static friction. Let's look at the deformation. So I need to, let's get the right, let's zoom in a little bit. And let's see, we're going to warp by a factor of, let's say, I want to value, let's do 20. And I should make a comment here that, remember our traction amplitude, our compressive stress was 120 megapascals, our shear components were 75, increasing up to 100. Those sound like reasonable values when you're down about 5-10 kilometers in the earth. Here with this bar, with this shear wave speed of 1 kilometer per second, those are really big traction values. And so we're going to get slip rates on the order of 10 meters per second, and so and slips on the order of 20 meters, and that's just because of basically the size of the tractions that we applied relative to our shear modulus. So here I'm going to step through this. So you'll see we exceed our friction threshold, we start to deform. Notice that in this dynamic problem, rather than the deformation immediately reaching the edges of our domain, the deformation is being transferred by the seismic waves, and so the ends of the bar don't move until the shear wave can propagate down the bar. I should color this. So let's color it according to the y displacement. It's odd that I don't get my y displacement. Let's see the change component for the velocity. There we go. Let's do velocity. So here's our velocity. Propagates down the edges. I rescale my velocity out this time step. You'll notice that things are almost uniform and then we're going to go into a steady state solution here of things propagating at about 11 meters per second. And this is the steady state solution. When I impose a traction and cause slip, the greater than what the friction threshold, I end up with the absorbing dampers opposing the deformation due to and there's a analytical solution for this, that the traction I'm imposing is balanced by the friction coefficient as well as the strain within the bar and the stresses associated with that strain. That is also has to be consistent with the stresses applied at the end of the bar are proportional to the velocity, and so we can solve for the velocity as a function of what the difference between the tractions I've applied and my friction tractions. Static friction is quite easy. Slip weakening, I go to the dynamic value, and so I can compute what that is. Rate and state friction, my coefficient of friction parameter depends on the velocity, so I end up with a highly nonlinear equation that would need to be solved numerically to get what the steady state solution is. So this is the static friction case with our time-dependent traction applied. Any questions on this example before we go on to rate and state friction? Running this same problem. Okay, so we're going to keep that in pair view so we can compare our static friction with rate and state friction. So let's pull up our spontaneous Rupp rate state. And remember our static friction, all we did was specify what our friction parameters were and then our output file name. So that's the same thing we're doing in our rate and state case here. We're changing from our friction constituent model to rate and state aging, give it a name of rate and state for our label. Here's sort of in comments what our parameters are for rate and state friction. We're going to use a reference coefficient of friction of 0.6, reference slip rate of 10 to the minus 6, slip weakening parameter of 2 centimeters, value of A of 0.008, value of B of 0.012, a cohesion of 0. We're going to use a uniform database to specify those. And so here's what it looks like in terms of uniform database. We have to write out all of our what the values are in the spatial database so that we have the order and we can line up these values with our values that we specify up here. So 0.6, 1 times 10 to the minus 6 meters per second, 0.02 meters, 0.008 A and B are non-dimensional, and then our cohesion a value of 0. For rate and state friction, we're going to give it an initial state variable that's consistent with what the coefficient of friction is going to be for an applied, for essentially 0 slip rate with our applied tractions and our initial value of our state variable with 0 slip rate is consistent with a state variable value of here it's 1.606 times 10 to the 9 seconds. With rate and state friction, you have to be more careful about setting up your problem. If you're trying to start from a steady state solution, you need to make sure that your initial conditions and initial state variable are all consistent If you don't start from the steady state, you may want to sort of spin up your model so that you get to steady state before you start deforming the boundaries. And so then you just maybe turn on your loading at, say, well into the simulation rather than right at time step 0. And again, we specify what our output file names are. So it's quite straightforward in terms of our friction properties and the differences between this one and the static coefficient of friction case. So to run this, spontaneous disrupt.cfg, spontaneous disrupt rate state aging.cfg. And I should highlight again that with Pilot 1.9, we've greatly improved the robustness of explicit time-step and rate and state friction. We are now confident that we have a stable sort of solver implementation of that with a Newton-Raphson in log slip space to get the consistent coefficient of friction for a given slip rate. And so we've run some benchmarking cases with the SCEC dynamic rupture benchmark to verify that. We compare very well with other codes. Before, we essentially just had a robust implementation for the quasi-static case. So now let's load up the rate and state aging. We're going to do the same warping. So in this case, so I'm going to warp, and I believe I did a factor of 20. So let's verify that in factor 20. I'm going to color the previous, I'm going to color the static one. Let's pick a, oops, I need a solid color. So let's use a nice bright green for our static case. For our rate and state case, we'll go with, let's go with blue. And so if you'll notice that at time step 0, we're immediately on top of each other. And here, my static coefficient of friction is responding quicker. I'm getting initially more deformation. And then my rate and state starts to deform later, and you may be asking, why is that so? Well, in rate and state friction, that the term with the A in front of it is called the direct effect. And as you start sliding or increase your slip rate, the coefficient of friction actually increases. Then once you sort of start to get towards a steady state value, then you go towards a value given by A minus B, and in this case we set it up the fault to weaken. So after we have sort of the direct effect and it decreases with time, then the weakening kicks in, and we'll see how that plays out. And so initially we start slower than using a static coefficient of friction 0.6 because of the direct effect. As we weaken, you'll see here we're going to actually catch up to the static case, and then we'll exceed it because we have a larger velocity due to the fact that the fault weakens, and so our coefficient of friction is below 0.6. And in both cases, we're going to get steady state behavior, and so with the faster velocity, greater weakening, I end up with more strain in my bar because I need to still exactly counterbalance my prescribed tractions. So there's the rate state case in blue and the static friction case in green. So I'll show you that again. Again, sort of our rate state with the direct effect takes a little longer to get going, but then it's going to catch up, and with weakening, it's going to surpass our static friction case in terms of velocity. If I plot the velocity here, we scale it. Velocity of magnitude, that's not right. What did I have? I think it's scaling off of my initial value. There we go. So here I am at Before, in our static friction case, we had a velocity of around 11 meters per second. Here I am up at around 14.5 meters per second. Any questions on the rate and state case or friction in general? Any general questions regarding pilots and how to get going? Are people running examples and successfully, or are people getting stuck? Do you have questions on how to move forward? I expect this afternoon we'll probably have another in our last session, where there'll probably be about, so I see a question. Can you type it into the Q&A panel? Is it too long of a question? Can you give us feedback there on the chat window? I don't see any evidence of type up. You're trying to talk, and I've muted your microphone, so hold on just a second here. We'll give this a try. So I need to